The next case study I'm going to discuss is also a commercial building, but it's a 24/7, 24 hours a day and 7 days a week use building. The building again is located in Delhi NCR with a total built up area of approximately 50,000 square meter. The building had deep plan offices, so the daylight was only limited to the perimeter of the building. Perimeter spaces are the spaces which are next to the building envelope or building facade. The spaces which are inside those or spaces which are too deep were not able to receive good daylight. The building was ground plus 9-story high, having 2 basements, and the client aspired to achieve platinum rating, platinum IGBC green new building rating for this particular project. Again, we started the project with a facade solar radiation study. On your left are showing you a building plan, how the building was planned to be in complete development. The project had 2 phases, phase 1 and phase 2. Front of the plot, which was facing the main road, was planned to be in phase 1. However, the master planning studies were done for both phase 1 and phase 2. The project was observed that the front facade was actually the north facade, and that's where through solar radiation we validated that we were getting the minimal amount of solar radiation falling onto that surface, onto the north facade, while east, west and south were getting relatively much higher radiation as expected. Roof was obviously getting the maximum solar radiation, which could be developed for optimizing or harnessing solar energy through solar PV panels. We developed the energy model for the project. You would see that the project was designed to be like a glass box, which primarily had glass on all the 4 facades with having more than 80 to 90% window to wall ratio. These are the parameters which were considered. If it's a conventional building, what will happen, what is generally used, shown here as building as usual, with all the parameters for brick walls, roof having brick bat koba. Typically business as usual buildings have 20 to 30% window to wall ratios, but this building was having more than that. This was having almost 80 to 90% window to wall ratio. In comparison to that, when we compare ECBC values, U values for walls, roof are much more stringent as compared to business as usual. The window to wall ratio is also limited to 40% as given in ECBC 2017 as well. All the values, all other values were majorly much more stringent in ECBC. I won't be going through the lighting and the equipments and air conditioning part of it, as we are not focusing on it. We are majorly focusing on the building envelope and the facade strategies. So, through building simulations for this particular case, we realize and we showcase to the client how having such high window to wall ratio could really have a detrimental effect and poor performance of the building. We showed them how if we further reduce the window to wall ratio, the amount of glass on the facades, how further we can reduce not only in the energy performance index, the energy consumed per square kilowatt hours consumed per square meter per year, but we also showed them how it would also reduce the overall chiller tonnage or the air conditioning load. So, if our chiller tonnage or the air conditioning load is also significantly reduced, that will also help us in reducing the capital cost of the building, not only the operational cost. So, the case study, the simulations done showed that if the window to wall ratio was optimized somewhere around 30 to 35%, that would be the tipping point in the project, where between 30 to 40%, that is the most optimal solution for this particular project. If the window to wall ratios are reduced below 30%, the energy savings would start reducing. The reason for that is the daylight ingress in the building will start reducing significantly in the areas which could be potentially well daylit, and that would lead to more use of internal artificial lighting. So, as a guideline, the study showed that having window to wall ratios for this particular project between 30 to 40% would be more optimal, and that would also help the client to reduce their chiller size in this particular project by almost 175 tons. Further, we showed what would be the impact of solar heat gain coefficient or the heat gain those windows in the project. We started with having SHGC of 83%, which is for a 6 mm clear single glazing, and checked different glass options available to us with reducing solar heat gain coefficient from single glass to double glass. We realized that the relationship between savings in energy consumption of the building and tonnage is quite linear with comparison with in correlation to solar heat gain coefficient. The more SHGC we reduce in the project, lower would be the energy consumption and lower would be the heat gain. Further, we also checked what would be an impact of glazing insulation on the energy performance of the building and the heat gains. It was observed in the project that the heat gains or the energy consumption, because of the U value, would saturate almost after we achieve R value of 2, which was also an ECBC recommended glazing value, glass U value. Beyond that, if we keep on increasing the insulation, the savings were not significant, either in terms of energy savings or chiller tonnage savings. For the wall insulation, for the facade insulation and wall insulation, we checked where do we fall in comparison to ECBC recommended prescriptive values, and 250 mm AAC brick wall or masonry work, which was proposed ultimately in the project. It was proposed primarily because through these simulations, through these graphs that we are presenting here, we realized that after beyond 10 R value, the savings were not as much significant as much they were before, and even reaching to a point where the insulation is matched to ECBC prescriptive value, it will not lead to significant energy savings. However, capital cost gains would be significant, capital increase in the project cost would be significant. So, recommended to the client to stay with 250 mm AAC blocks, which would give us R10 value in the project. As a summary of the studies conducted for this particular project, we realized that if the project been a conventional building, having all the conventional building parameters like 9-inch brick wall, non-insulated roof with just brickbat coba on top, single clear glazing and on, the project would achieve an EPI value, energy performance index, kilowatt hour per square meter annually. The consumption would be 436 kilowatt hour per square meter. However, through different facade optimization strategies like good daylight harness, by probably integrating daylight sensors in the perimeter spaces, by insulating roof, by having high reflective finish on the roof, by using AAC wall on the AAC block work for the exterior walls, having high performance DGU for the windows and for the glazing, having SHGC solar heat gain coefficient value of 25%, and further improving the solar heat gain coefficient by having horizontal shades on south, east and west facade of 1200 mm deep, and reducing our window to wall ratio to 30%. With all those strategies, we could reduce our energy performance index or building energy consumption from 436 kilowatt hour per square meter to 347 kilowatt hour per square meter. This also reduced our building envelope load from 13.8 watt per square feet to 2.8 watt per square feet, and the chiller size would be reduced from 280 square feet per ton, which is generally there for a conventional building, to almost 400 square feet per ton. So, with these strategies, with only strategies involving facade, we could reduce the chiller tonnage to 400 square feet per ton, which is in my opinion quite well performing. Moving on to our case study 3. This is also a commercial core and shell building located in Delhi NCR. This had a total built up area of approximately 1000 square meter with building height ground plus 8 and having 2 basements. This particular project is aiming 5-star GRIHA rating under version 3. We started through, so I'll just quickly take you through the third case study, just showing you what we had initially. So, when the architect gave us the project, the project was receiving only 65% area which was achieving well daylight. This was the area which was receiving good daylight between 110 lux to 2200 lux. However, the project also had significant glare problem from the south and western facades, which must be optimized in order to really harness good daylight in the building and to improve the energy efficiency of the project. We realized that we showed to the client through the glare analysis that we can see that on summer solstice there was significant glare coming in from the south and the west facade. The east facade also had little glare, but that glare was not really a problem for this project, since this project was an office building and the glare was only there till 9 or 10 am, and typically office buildings start working after 10. So, we were not really so much concerned about glare from east. So, as a repercussion, after many iterations and many design solutions, we reached to a level where we proposed to the client an origami inspired external shading device. The shading devices would be static. These are not dynamically operated shading devices. The shading devices were designed to have at least around 40% open views, so that the views are not 100% blocked for the people who are sitting inside, while the shaded area would be more than 62%. And on this slide we show you how the original design looked, and with the proposed facade it would actually have a better aesthetical statement, and this facade would also work well. The studies here would show you how we were receiving almost minimal glare or negligible glare during office period from south and the west facade in both June and September. While in December there were a little glare, but again, as we realized that in the month of December or during winter, outside conditions are primarily foggy and there won't be much direct sun available. So, this is not really a problem. So, for with this design, the glare was prevented and zero glare was observed for more than 90% period in the project with the proposed facade. The project was achieving 97% well daylit areas receiving more than daylight between 110 lux to 2200 lux. In the proposed design, we were not required to go with the high performance DGU. A clear double glass was proposed, as the external direct solar heat gain was primarily prevented, or the external heat gain was primarily prevented through external shading devices. So, tinted glass or high performance double glass was not really required. This kind of clear glass would have a VLT of 70%. Fenestration, the overall effective fenestration SHGC was calculated to be only 5%, which is much below even the ECBC recommended 25%. The internal blinds were not at all required in this particular building design, as the external shading devices were quite effective. And like I said, receiving more than 97% area getting 110 to 2200 lux. Only 3% areas were getting more than 2200 lux, which was next to the southern eastern facade because of the clear DGU glazing. With this, I will be concluding this session. I believe the takeaway from these case studies are that, one, we need to go for integrated design approach. An integrated design approach not only looks at the energy performance of the building, but also looks at a good, well daylit interior spaces with good quality daylight, not just high amount of daylight which where glare is a problem. So, well daylit spaces with zero glare and with good energy performance would lead to a good performance facade, which can only be achieved through integrated design approach. For an integrated design approach, we definitely need building simulation tools. These tools help us predict the performance of the facade and the building in advance, and not leave us to the end product later, where the building is built and then we realize that the facade is not performing. So, we can actually prevent such cases through building simulations. They are a really good tools that we have available in the market. And thirdly, EC/BC prescriptive requirements which are given to us as a guideline, they are quite effective in actually achieving a high performance building facade. However, by using building simulations, we can negotiate with those values, still have high performance values while minimizing the overall project cost. Thank you.